Hi everyone, I'm Shreyansh Pitroda and I'm here to present the paper called Capture Point Control in Thruster Assisted Bipedal Locomotion. This project is in collaboration with Northeastern University and California Institute of Technology. The project is funded by NSF Foundational Research in Robotics Grant. This slide shows the contributors who have contributed towards this paper. On the left-hand side, Dr. Reza Ramzani is PI from Northeastern University. He is an associate professor in Department of Electrical and Computer Engineering. Dr. Mordeza Karib, he is from California Institute of Technology. He is a professor and director of CalSite and Cast Matters. All the PhD students, Shreyansh Pitroda, myself, Adarsh Salgami, Chengao Wang, and master student Tauran Liu from Northeastern University. Dr. Eric Sehiti from California Institute of Technology. He's a postdoc research associate there. Uh, Aditya Bondada from Northeastern. He's an MS student. Vivek Gupta. He's also from Northeastern. He's a PhD student. Kaushik Venkatesh Krishnamurthy. And Reza Naomi. He's from California Institute of Technology and is a research engineer. This slide gives a brief overview on Harpy platform. Harpy is a multimodal robot. It has two thrusters connected to its torso. Each thruster can produce a thrust force of about 5 kg. The overall weight of the robot is about 6.5 kg. It has 6 powered in joints, 2 for frontal, 2 for sagittal, and 2 for knee. Each joint is custom made from harmonic drive and motor assembly. It also has a spring connected to its ankle in a series elastic actuation formation. It has sensing elements such as thermal camera, IMU, interrelations camera, and joint encoders, and some control elements such as Jetson O-ring, which is connected to thermal camera and interrelations camera, Alma amplifier, which is connected to joint encoder and act as a low-level controller for joints. It has an STM plus NetX shield, which is connected to the IMU. All of these controllers are connected in daisy chain formation, and they are further connected to the speed code, which acts as a high level controller for this platform. On the left hand side, we can see jump and drop test performed on single leg of Harpy and also has a thruster connected to it. This leftmost video shows the impedance control done on Harpy, and then it also shows a drop test where the robot is made to fall from a particular height. And from the video, we can see that the spring and then the joints are able to take up the load properly. On this video, we can see the jump test performed on Harpy, where it jumps using the joint torque and the thruster forces as an impulse load, as an impulse thrust. Using this two combination, it's able to jump up to 0.6 meters height. This slide shows that despite the major advancement in control design framework that are robust to unplanned disturbances, bipedal robots are still susceptible to fall over, and it's really tough for them to negotiate rough terrains. Thus, in this paper, we extend the capture point dynamics by including the thruster forces into the dynamics. This slide shows the state-of-the-art robots, starting with traditional legged robots such as Spot, Cassie, and Animal. These robots are able to traverse through uneven and rough terrain using its legged locomotion and some robust and complex controllers. Then there are multimodal robots such as Leonardo, which has propellers connected to its torso and legs. It was able to show capability of walking up on a thin rope or slacklining using its propellers. Then there is Salto robot or Salto 1P, which is a hopping robot. It hops from one place to other, and while it's in the aerial phase, it's able to stabilize itself by use of thrusters or by use of propellers. Then there is M4 robot, which is a wheel robot, which also has propellers connected onto its wheel. M4 is able to go in this Segway mode where it can balance itself on two wheels by the use of the propellers and can go up in a steep slope. High fidelity modeling or finding the nonlinear dynamics for our model. The figure on the right hand side shows the high fidelity model in the SimScape environment. This figure shows the inputs, the joint positions, COM position, and then the link lengths. Total robot has 12 degree of freedom, 6 for body and 3 for each joint. For formulating or for finding the nonlinear dynamics, we start with finding first the forward kinematics for the robot. Then we go ahead and find the kinetic and the potential energy. And then we use the Euler-Lagrange formalism to find the complete nonlinear dynamics. This equation shows the nonlinear dynamics for the robot, where m being the mass in the inertia matrices, a is the acceleration of the robot, h has Coriolis and gravity terms, uj, ut, and ug are the inputs, and bj, bt, and bg are the matrices which maps these inputs to the acceleration. Completing the full nonlinear dynamic modeling, we go ahead with deriving the reduced order modeling. So this figure shows the reduced order model for Harpy, which is a vertical linear inverted pendulum model. PB is the center of mass position, UT is the thruster force, R is the length of the pendulum, and C denotes the C denotes the center of pressure point. Next is the finding out the equations of motion for the reduced order model, where PB double dot is the acceleration of the center of mass, and G over here is a vector which is 0, 0, and G. UT is thrust of force, and JS transpose into lambda is the constraint force. This constraint force makes sure that the leg length R is equal to the leg length leg conformation. From that, we get the constraint equation, which is JS is PB minus R, PB minus C transpose, and JS into PB double dot minus C double dot is equal to QR. Deriving the equation of motions for the reduced order model, we go ahead with deriving the capture point for the VLIP model. For this, we project the VLIP model onto two planes, that is the frontal plane and the sagittal plane, and then we derive the equations for the sagittal plane. This shows the equation of motions for the x direction and the z direction. For the capture point, we make an assumption saying that the height of the pendulum will be fixed. That is, z0 is constant. That means that the acceleration in z direction will be 0. So if we substitute that acceleration is equal to 0, we can find the lambda from this equation and then substitute that lambda into the above equation. Posture manipulation, we can do thrust vectoring and make our thruster always point vertical. So we can say that sine theta is equal to 0 or theta equal to 0, and thus sine theta is equal to 0. And once we do that, we end up with this equation, that is PB double dot in x is equal to stiffness term into PBX upon G0. After this, we find the kinetic and the potential energy of the system and then equate that thing to 0 to give out the final capture point for the VLIP model in sagittal plane. We show the equation of motions for the VLIP model, which is this one. This term has negative stiffness, and the stiffness is dependent on the gravity and the thruster force, both. So this means that by increasing the thruster force value, we can make our system be more stiffer or more buoyant. And for this purpose, we did an experiment in our SimScape model and plotted the graph for it. So this graph shows that when we increase the thruster, that is g dash equal to 4 meter per second, which is this one, the system has to take a smaller step length than when we have no thruster, which is G is equal to G dash is equal to G, which is this one, it has to take a longer step length. So this clearly shows that if by addition of thrusters, we can make the system more stable and it will be less susceptible to fall and external disturbances. The simulation results for Harpy. Uh, in this, Harpy is walking on a flat ground. The axis is oriented in such a way that y is pointing back, x is pointing towards this, and then z is pointing upward. Harpy is stabilizing itself in the sagittal direction by using the capture point, and then frontal direction is stabilized by the thrusters. This snapshot of Harpy walking on a flat ground. From the COM trajectory or PB, we can see that the robot is not deviating so much from its path. C over here represents the COP point or center of pressure or the stance foot. UTC shows the thruster forces. The thruster force is activated in such a way that whichever is the stance leg, we activate the opposite thruster from the stance leg. So as in from this one, we have left as a stance leg, so we activate the right thruster. This is done because we cannot have a negative thrust value. So to provide a negative movement opposite to the fall, we use this thing. And the capture point is actively getting generated to stabilize the sagittal motion, while the thruster can take care of the frontal motion. Of Harpy, from the body position, we can see that the robot was moving forward, and it was not deviating so much on the x direction because it was stabilized by the thrusters, and then the same for the z direction. From the body velocity, we can see that the body velocity is not changing rapidly, or it's not fluctuating too much. That means the robot was stably walking forward. The same could be seen from the Euler angles as they are not changing drastically, and also the angular velocities. The thruster forces used by the left and the right thruster. From this graph, we can see that at a time, only either a left thruster or the right thruster is activated. And then the maximum thruster force used is 20 newtons, which is well within the hardware limits. Ground reaction forces for the experiment that we performed. From this blue curve, we can see that the robot is able to follow a symmetric gait. And then the darker blue dot shows the left leg contact, and the red dot shows the right leg contact. The arrow in the upper direction shows the normal forces. In conclusion, we employed a control design strategy based on the capture point, including the thruster dynamics. The controller was quickly able to attain a stable limit cycle, which shows its effectiveness and the efficacy. Last, the high fidelity model in the Simscape environment allowed us to do a detailed analysis on the system's dynamics. For future work, we need to perform using a controller. We need to perform experiments on a more dynamic environments or more dynamic situations, such as when we have an uneven terrain or when we have some external disturbances. And lastly, we need to use our controller and do some experimental validation of our controller. My presentation, and kindly let me know if you have any questions.